Okay, so in the last video we defined the notion of a sequence of rational numbers that is bounded away from 0, and we proved this result that if we are given a non-zero real number, then there exists a Cauchy sequence of rational numbers that is bounded away from 0 and whose formal limit is that real number. Now our ultimate aim here is to, of course, define the reciprocal of a non-zero real number. So in that direction, this result gives us a step. The next step starts from here, namely that we are given a Cauchy sequence of rational numbers that is bounded away from 0. Then we have to take the next step, that is we form the sequence of reciprocals of these terms in this sequence, and the result we are now going to state and prove is that this sequence is also a Cauchy sequence. So this gets rid of the problem that we previously encountered, namely where we say considered this sequence and it turned out that the reciprocals don't form a Cauchy sequence. So that problem now is not there, and once we prove this result, we will then be able to define the reciprocal of B to be the formal limit of this sequence. So let us first prove that this sequence is a Cauchy sequence. So the specific statement is this: this is lemma 15. Suppose that an is a Cauchy sequence of rational numbers that is bounded away from 0. Then the sequence is also a Cauchy sequence. Okay, so let us now see how we can prove this result. So in the beginning, since we have to show that this is a Cauchy sequence, so we will start by choosing epsilon. Let this be any positive rational. Since the given sequence is bounded away from 0, there exists a positive rational number C such that all these absolute values are greater than or equal to C. And this is the reason why we are able to take reciprocals of all the terms, because none of them can now be equal to 0. Next, since we now use the next piece of information available to us, since this is a Cauchy sequence. So there exists a positive integer, say n, such that the difference between an and am, numerical difference or distance, is less than or equal to, say, c square times epsilon for all n and m greater than or equal to n. The question is, why c square times epsilon? That we will soon realize. We have conveniently chosen c square times epsilon. This will help us afterwards. We can choose c square times epsilon. Note that, that is important also. C is a positive rational number and so is epsilon. So c square epsilon is also a positive rational number. So it can be chosen to be the number here. Okay. Now, for any integers n and m, both at least capital N, we have, let us now estimate the size of this distance. Difference between the reciprocals. This is equal, I think it will be better to put some ink first. One over an minus 1 over am. So this, if we manipulate this expression, it becomes, in the denominator we have the product of these two absolute values, in the numerator we have this. Okay. Now this difference is less than or equal to c square times epsilon. And what about this quantity? Its absolute value is greater than or equal to c. Since both of these are positive rational numbers, we can take the reciprocal of both of them. The inequality will get reversed. So 1 over absolute value of an will be less than or equal to 1 over c. And a similar one will happen for this one. And note that these inequalities are true for any value of the index. N can be any integer, any positive integer. So for this particular n and m also we will have the inequalities to be true. So we now have this, which is equal to epsilon. So that is why we chose c square to ultimately conveniently have epsilon. So we have proved that if n and m are any integers greater than or equal to n, then this distance is less than or equal to epsilon. So that just proves that this sequence is a Cauchy sequence. So you can write here, hence an inverse is a Cauchy sequence. Okay, now we are ready to define the reciprocal of a non-zero real number. And the definition goes like this. Reciprocals of real numbers. Let x be a non-zero real number. Let an be a Cauchy sequence of rational numbers that is bounded away from 0 and such that its formal limit is x. And this is where we are actually using the result from the previous video. Such a sequence exists by lemma 5.3.14. Then we define the reciprocal by the form. Oh, we need to mention the reciprocal of x to be this formal limit. And to make this meaningful, we take the help of the previous result. From lemma 5.3.15, we know we know that x is a real number. But our job is not done yet, because note that unlike the previous operations that we defined, I mean towards the end, after defining addition and multiplication, which we proved to be well defined, the other operations of negation and subtraction, they were defined in terms of addition and multiplication. This is a new situation. Here we have got down to the basic level of Cauchy sequences of rational numbers, and then with the help of them we define the reciprocal of a non-zero real number. So again we need to see that this definition is also well defined. Namely, if we have two real numbers that are equal, which are possibly given by different Cauchy sequences of rational numbers, but which are of course equivalent, that's why the real numbers are equal, then their reciprocals also have to be equal, because we know that the original sequence of Cauchy sequence of rational numbers that defines x is not being used in this definition. The only thing we know is that once a non-zero x is given to us, then there exists a Cauchy sequence of rational numbers that is bounded away from 0, whose formal limit is also equal to x. The existence of this an is only an existence which we proved in a previous result, namely here in this lemma. However, for this given x, this an is not necessarily unique. So who knows, maybe there is some other Cauchy sequence which is also bounded away from 0 and which happens to have the same formal limit, namely that sequence is equivalent to an, this sequence. Then will this process of defining the reciprocal using those two sequences give us a single real number as the reciprocal? If that is not true, then our reciprocal is not well defined. So we will now have to show this, that actually it is well defined. So for that we have this result next. Let an and bn be two Cauchy sequences of rational numbers that are, both of them are bounded away from 0. And are such that their formal limits are the same. That is, which means that the sequences are equivalent. then these two formal limits are also the same. Once we prove this, then reciprocal will be well defined for us. For this proof, however, the proof is a little clever and hence somewhat more beautiful than the other proofs. So for this, consider the product. Consider the following product P of real numbers. And the product is defined to be this. It's a product of three real numbers, that is three formal limits, and they are this. Limit of an inverse, then limit of an and limit of Bn inverse. Okay, now if we just simply apply the definition of product of real numbers, then P will be equal to this formal limit which, given the fact that each an is a non-zero rational number, so these two will cancel out, leaving us with Bn. On the other hand, since we have our original formal limits to be equal, so we have at the same time P also equal to in place of this we will write limit of Bn. So this, by the definition of product of real numbers, is equal to this formal limit, which turns out to be hence So that proves our claim. So now reciprocal is well defined for us. Now the only thing left for us to do is we are now required to make some observations about reciprocal, this operation of reciprocation. Thus, reciprocal is well defined, that is, there exists exactly one reciprocal. Note that reciprocation is like negation. It's a function as opposed to a binary operation. Binary operations are also functions, but it's a function where there is only one input. In a binary operation, you can think of it as a function with two inputs, like for instance, addition and multiplication are binary operations. So the fact that this is well defined just simply says that the function is well defined. That means for a given input there is exactly one output. That's why we are writing for each non-zero real number x there exists exactly one reciprocal, which we have now proved. Note that from the definition of x inverse, it follows that x times x inverse is equal to x inverse times x is equal to 1. How are we directly writing these relations? It's because you see, if you have x which is given to be non-zero, a non-zero real number, then you have found a Cauchy sequence of rational numbers an that is bounded away from 0 and whose formal limit is x. Then according to our definition of reciprocal, this is just this formal limit. So now if we take the product of x and x inverse in any order, say let us take x inverse, then by the definition of multiplication of real numbers, it will be this formal limit, which is the formal limit of the constant sequence of rational numbers, all of whose terms are equal to 1. And because of the way we identified rationals inside the reals, this is equal to 1. So that's how we are getting the fact that when you multiply a real number with its reciprocal, you get 1 in any order. So only defining the reciprocal was somewhat problematic, and we had to devise some methods for doing that. We had to get around the problem of having non-Cauchy sequences. If we just simply take the reciprocal of each term of a Cauchy sequence, and for this we had to devise the notion of a sequence bounded away from 0. But after we have the fact that okay, reciprocal exists and reciprocal is well defined, then the rest of the calculations are just easy and straightforward. Thus, the field axioms, that is proposition 4 which says that the system of rational numbers with its addition and multiplication and reciprocal everything is a field. Just like that, the system of real numbers is also now a field. It has been proved. Apply to the reals as well as they apply to the rationals. There is one more observation. But before that we have to just simply mention we cannot define the reciprocal of 0. Because the product of 0 with any real number is 0 and not 1. You can very easily see why such a product is 0, much like how we saw why these relations are true. Say you have a real number. Here you don't even need a Cauchy sequence that is bounded away from 0, because now it's not about taking reciprocal. X is any real number which say is the, by definition, the formal limit of a Cauchy sequence of rational numbers. 0 as a real number is the formal limit of the Cauchy sequence of rational numbers, all of whose terms are equal to 0. So if you multiply 0 with x, then you will have this by the definition of product, which is equal to the formal limit of this constant sequence, which again from our identification of rationals within the reals is equal to 0. So if you somehow by some definition you define the reciprocal of 0, multiplying that reciprocal with 0 will never give you equal to 1, because if according to your definition the reciprocal turns out to be a real number, then this calculation shows us that the product is always 0 and never equal to 1, so that these relations will not be true if reciprocal of 0 is allowed, and that's why we do not define reciprocal of 0, or we do not divide by 0. Division by 0 will be allowed in a sense later on when we when we see measure theory. But we are still far away from that. And one more important observation is this. Also, note that if Q is a non-zero rational number, then we want to say that the definition of taking the reciprocal of Q when you think Q as simply a rational number is the same as taking the reciprocal of Q when you think Q as a real number. And the reason is this. Then the reciprocal of Q when Q is viewed as a rational number is just this, whereas the reciprocal of the real number Q. According to our identification, Q is thought of as the real number, which is the formal limit of the Cauchy sequence, all of whose terms are equal to Q. If we are thinking of Q like this, then according to our new definition, that is reciprocal of a real number is which again is a which again is a constant sequence of rational numbers. So according to our identification, it's equal to this. So we get the same thing. Thus, operation of reciprocation on the real numbers is consistent with the operation of reciprocation on the rational numbers. So whether we think of a rational number as a rational number or a real number, it does not matter. You will get the same reciprocal. And now one final thing, just like using negation and addition you can define subtraction, we are now going to use reciprocal and multiplication to define division. Something that we already did in the system of rational numbers. Now for real numbers we are going to do. Now that we have reciprocal we can define division of real numbers as follows. Let x and y be real numbers such that y is non-zero. Then we define x divided by y to be the product of the real numbers x and y inverse, where y inverse is the reciprocal of y and xy inverse is ordinary multiplication of the real numbers x and y inverse. Recall that we similarly defined already wrote defined similarly defined division on the set of rational numbers Q. And finally, we thus have the cancellation law. If x, y and z are real numbers such that xz is equal to yz and z is non-zero, then x is equal to y. You can cancel z from both sides. To prove this, you may already know this. You start with this equation, then on both sides you multiply by the reciprocal of z. That and z cancel out, leaving you with x and y. So that gives you that equation, x equal to y. Note that the cancellation law is not true when z is 0. If z is 0, then from equality of xz and yz, you cannot say that x and y are equal. And it's very easy to see why. And the reason is this: 1 times 0 is equal to 2 times 0. On both sides we have 0, but here z is 0. So you cannot cancel z from both sides and claim that 1 is equal to 2, because that is false. So non-zeroness of z is important in the cancellation law. So with this, the list of results are over in this section. In the next video, we will look at the exercises. So I end the video here. So see you in the next video. Have a nice night.